Okay, recall that if S is a subset of V, then the span of S is a subspace of V. And what we want to do is figure out how to find the basis of this vector space, this subspace. So we'll start with a couple of examples that we can do just by geometric reasoning and thinking about stuff. And then we'll do some, after that, we'll do some additional examples that require us to do some calculations. So this first one, find a basis of span of 1, 2, and negative 3, 6. So if you think of these are two vectors in R2. 1, 2 does this. Wait, no, that's not quite right. 1, 2 goes over 1 and up 2, so it's here. Negative 3, 6 goes back 3 and then down 6. So it's like that. So if you look at these, they really only span a line. And the second one is redundant. So we can toss really either one of these and come up with a basis. So a basis of this would be either 1, 2, or you could say, you could throw away the 1, 2 and keep the negative 3, negative 6. So those are two different bases of this vector space that we're looking at, just a set of vectors that lie on this line. Now, those aren't the only ones. You could also use anything else on that line. You could say the set with just 2, 4. That's also a basis, and so on. All right, now let's look at this one. This is a subspace of R3, spanned by 1, 0, 0, 0, 0, 3, and 505. Now I'm going to draw in my three-dimensional axes here, X, Y, and Z. So if you look at this 1, 0, 0, that has a 1 in the X direction, so that's this vector. 0, 0, 3, that points up 3 in the Y direction. I'm sorry, in the Z direction. That one should technically be longer than the one going down the X, but close enough. Thing is, that right there is enough to get you everything that's in this plane over here. Now, 505 points up here, but it still lies on this plane. So for this, we could, again, we've got three vectors that lie on the same plane, and so it's a two-dimensional subspace. So in order to get a basis, we just have to throw away one of those three guys. I'm going to throw away the 505 and get this for my basis. But it would be just as correct to throw away the middle one and keep 1, 0, 0, or to throw away this one and keep the other two. So there are several different answers there, and actually, you can pick any two vectors that lie in that plane, and that would be a basis of this subspace. Okay, so those are ones we can just kind of look at. But if we do a more complicated example, we're going to have to do some calculations for it. So let's look at this. Find a basis of the span of these guys in R4, where we've got these four vectors. All right, now just looking at those, R4 has subspaces that are dimensioned 1, 2, 3, and 4. So just looking at this, there's no way to just look at it and tell, unless you're like truly gifted at spotting linear combinations. So here's what you do. You take each one of these and you put it into you make each one of these guys a column. And then you row reduce it. And the row reduction is going to sift out anything that's a linear combination. So let's put this in an octave. And I noticed something right off. We've got two rows that are exactly the same, but row reducing will take care of that. All right, is that correct? 9, 10, 10, 2. Yeah, that's good. So when I row reduce this thing, I get this. Let's see, 1, 0, minus 1/3, minus 1. I'm going to include another, I'm going to augment this with zeros. And 0, 1, 2/3, -2. And then everything else is zeros. I'll fill them in no particular order. All right, so we've got that. And then the leading ones over here, I meant to do that in purple. The leading ones over here tell us which columns over here are linearly independent. So these free variables, those say that these can be generated by using the first two columns. So anyway, what we do is we only keep the vectors that correspond to the leading ones over here. So our basis is going to be -9, 10, 10, 2, and 0, -1, -1, 1. Now, if you had taken these and put them into the, if you had put these into this matrix in a different order, like I just put them in the order they were given, but if you rearrange the order, you might get a different basis, but it would still be a basis of this subspace. All right, let's see. We've got two more examples. The rest of these, they really work exactly the same. It's just we're dealing with different stuff here. For this one, the matrix we're going to have one column for each of these. And again, I'm going to use this ordering. -2, -2, -8, 1, 9, 6, -3, 3, 11, 8, 5, 2, -8, 5, -1, -1, -7, 16, -5, 1. All right, so that's a pretty big matrix. Let's row reduce it. All right, let's stretch this out. All right, so we've got that. Does that look correct? Yeah, it looks good. So, all right. So we get all of this. Now I'm not going to go through and recopy this. I'm just going to look on my. I'm going to look here. So we've got a leading one in the first column, second column, not the third, fourth column, not the fifth. All right. So I'm just going to mark those off on there, and that gives me my basis. And I'm going to write this down as a basis for this is the set that contains the first, second, and fourth. So I'm just going to say U1, U2, and U4. All right. Last example. This one is going to be much the same way. Each one of these is going to give us a column. So this is going to give us 1, 0, 1, 1. This one is going to give us a column with 3, 0, -1, 2. And this is going to give us a column with just 2, 0, 0, 0. Let's reproduce this. All right. 1, 3, 2, 0. Then all zeros. Then 1, -1, 0, 0, 1, 2, 0, 0. Reduce that. We get a leading one in all 3 columns. So that means we need all of them. So the basis of the span of that is going to be, let's see, did I enter that correctly? I want to double check. Yes, it's not what I was expecting it to be, but this gave us a leading one in all 3 of those columns. So therefore the basis is going to be all 3 of them. Oh well. All right, and that's it.